So what we're going to look at today is simply molecular orbitals, and specifically we're going to deal with these three questions, A, B, and C. Our first thing we want to look at is the peroxide ion, so O2 minus 2. So this is a molecule that has two extra electrons. So the first thing we really look at is the electronic configuration of oxygen. Let's just do oxygen by itself. So we have oxygen, and the electronic configuration of oxygen is 1s2, 2s2, 2p4. Or if we were to actually do this in electron filling diagrams, we would have it 2, 3, 4. Now, we kind of have to go to the molecular orbital diagram here. And with the molecular orbital diagram, I'm not really going to focus on the 1s. I'm just going to do those two. So I write 2s, 2p. And to start with, I'm just going to switch to pencil first of all, but I'm going to write in what neutral oxygen would be on each side. So 1, 2, just like that. Now, in the peroxide atom, I have two extra electrons. So this is one oxygen. This is referring to one oxygen on the left side, one on the right. So what do I assume is happening is I assume that each one has an extra electron that I'm just adding in that middle 2p orbital. And that again is because of the ion. So if I were to have -1 like I will in a second, I would only put one in on one side. They do not have to be symmetrical because they're going to be involved interacting in the bond, so it doesn't really matter which side you had picked. So the next thing we should do is we have to label our centers. So every single time you do this, it will be pretty straightforward. You're going to have a single box. Single boxes are sigma bonds. So you write sigma, sigma. Sigma, you write the label of the orbital that you're dealing with. So I'm dealing with 2s. I'm writing it for both because they're mirror images. But the bottom talks about constructive wave interference, and the top talks about deconstructive wave interference, or as we call antibonding. And I denote antibonding with a star. I do the same thing up here. I have sigma 2p. I have sigma 2p star, being of course mirror images of each other. Now where I have a double, that means that I'm involved now in side-by-side overlap, or basically kind of an indirect overlap. It's still constructive interference here, so we're going to write pi 2p, but then it's possible for that side-by-side overlap to also be deconstructive interference, so we write pi 2p star. Now, what we will look at from here on in is we're just going to be filling them. So basically you take the electrons you have on the outer and you populate them inwards. And you always populate from the bottom up, and you try and make them all single, and then you make them paired if you have to. So I have 4, so I go 1, 2, 3, 4. As soon as this orbital is completely filled, I know that I'm involved in what we call bond order of 0. In other words, what we're going to come up with is that bonding doesn't take place in the 2s, and that's not a surprise. So we have 2, 4, 6, 8, 10 electrons involved in the p orbitals. So we start from the bottom filling up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of electrons on the outside come together and match up in the middle, forming electrons in the center, which is actually the molecular orbital. So this is a molecular orbital diagram if you're asked to do that. But that's not obviously everything that we need to worry about. So we have this thing called bond order. And bond order is very straightforward. Bond order is equal to 1/2 bonding electrons take away non-bonding electrons. So for example, for this middle one, I'm going to have a bond order equal to 1/2 1, 2 bonding, take away 1, 2, non-bonding, so I end up with 0. That basically tells us that bonding is not taking place, which again we've already talked about. But the bond order for the p orbitals is a little different. So number of bonding, 2, 4, 6. Take away non-bonding, 2 and 4. 6 take away 4 is 2 times 1/2 is equal to 1. So what that 1 indicates is that I will have a single bond take place between these two. And that's more or less what we would predict. So this is the bond order for peroxide. If we were to look at superoxide, we would basically just be removing one electron. So without doing all this again, I'm just going to take that extra electron off the right hand side, meaning that I have 2, 4, 5, 6, 7, 8, 9 electrons. So I'm just going to take it away from the last in. So if you take one away, you take the last one you put in away. So now, just coming down here, looking at O2 minus 1, the bond order is equal to 1/2 the number of bonding electrons, 2, 4, 6, take away 3, equals 1/2, 3, equals 1.5. So the question is simply asking us, explain why the peroxide ion, O2 minus 2, has a longer bond length than the superoxide ion. And it's very simple. The peroxide ion has more antibonding electrons, more electrons involved in destructive interference. So that's going to actually cause the molecules to separate more. The bond length will be weaker and therefore longer. However, the superoxide ion has less antibonding electrons, therefore the bond order is going to be higher, making that bond tighter and closer together. So for the next part here, what we're going to look at is we're going to look at part B. And it says the magnetic properties of B2 are consistent with pi2p molecular orbitals. We're talking about these ones here, being lower in energy than the sigma 2p. So basically what we're saying here with this particular problem is that this would be normally what boron would look like. So we have sigma, we have, I'm just going to fill this in. So we have 2s, 2p, 2p, 2s. So you have sigma 2s, sigma 2s star. I have sigma 2p, pi 2p, pi 2p star, sigma 2p star. So I have, this would normally be what we would see. With boron, boron's electron configuration, it is in period 2. So it would normally be 1s2, 2s2, 2p1. So when we're talking about magnetic properties, we're talking about this paramagnetism and diamagnetism. So paramagnetism simply means that there is an unpaired electron. So it basically doesn't have a partner. Where diamagnetism will exhibit itself in molecules that have no unpaired, or in other words, all their electrons are paired. So the question says the magnetic properties of B2 are consistent with the pi2pi molecular orbitals being lower in energy. So really what we're saying is that it's consistent with these orbitals, these double orbitals, the pi 2p being below the sigma 2p. So basically these two just being flipped. So let's look at what it should be based on everything we know so far. So once again, we're not going to worry about the 1s2. We know bonding doesn't take place there. And we also know from the little introduction that we have done that even the 2s sigma bonds and antibonding levels, their bond order is going to be 0. So we expect a bond order of 0 here. So we can kind of ignore this section. So the difference becomes in the 2p. We have one electron from each boron atom contributing to it. So normally what we would see is we have 1, 2 electrons, so we'd start to populate. And we would completely populate the sigma 2p, meaning that, but look, there is no unpaired electrons, they're all paired up. So this is what we would say this material would be diamagnetic. However, if the question is actually indicating that the magnetic properties, so when we expose this to a magnetic field, it behaves very similar to something that is paramagnetic. So the explanation that we have is I'm just going to take these out and I'm going to draw it the way that they say we think it is. So they think, and the reasoning behind why it would be lower is really not important right now. It doesn't really matter because they're just telling you that it is. So I have pi 2p and sigma 2p. They're reversed. Now when I take the two electrons, 1, 2, and populate it, I end up with 2 unpaired electrons, making this paramagnetic. So the question simply is asking you is experiments are consistent with this version? Well, if experiments are showing that this is a paramagnetic material, that likely means this happened. In other words, the 2 pi orbitals, 2 pi 2p orbitals are actually lower in energy than the sigma 2p orbitals. Again, reasoning behind why that might happen or how that might happen is relevant. At this level, it's just that we're looking at the magnetic behavior. So if sigma 2p was lower, we would see it paired up. It would be diamagnetic. But because they're unpaired, it is paramagnetic. So to answer this question, we simply explain that away in words and say that if the pi 2p is lower in energy, we end up with a paramagnetic material, and if it was normal or the way that we would normally draw it to start with, it would be diamagnetic. So that is part B. So now we're going to have a look at part C. So part C is we want to use a molecular orbital, just like we had before, and I'm just bringing back a fresh page so we can use oxygen again. But it says the O2 plus 2 ion has a stronger oxygen-oxygen bond than O2 itself. So we've already gone through and done this. So what I'm going to do is I'm just going to populate this with the electrons that we know that oxygen has. So this is just for O2. I'll just erase the label when I can to make this work. We also always have to label. We have sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi 2p star, sigma 2p star. So really what we're doing here is we're just starting exactly where we started with part A. We have oxygen. Oxygen has 6 valence electrons, so 2, 4, 5, 6. So the molecular orbital, at least on the outsides right now, is just looking at O2. So let's populate this just like we had done before. 1, 2, 3, 4. We have 2, 4, 6, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we're seeing that it is in fact paramagnetic. It does have unpaired electrons in this particular case. So what we're looking at now is the bond order. So again, I'm going to just ignore this. We've done that a few times now, so we know what's going to happen. The bond order for O2 is going to equal 1/2 the number of bonding, so 2, 4, 6, take away non-bonding. So 6 take away 2 is 4, is a bond order of 2. So just like we predict, we have a double bond or a bond order of 2 for oxygen because we know it is oxygen is double bonded to itself. Now, we're going to just alter this ever so slightly to try and get this to work out. So we have the oxygen 2 plus ion. So that means we're going to lose 2 electrons. So I'm going to just change the electron orbital that we have. So I've just erased 2 electrons, leaving 3 in each 2p. If we do that, I'm going to take the last 2 electrons out. The question says the O2 plus 2 has a stronger bond. So this is the O2 plus ion. That would be the molecular orbital for it. So now we write the bond order for it of O2 plus 2 is equal to 1/2, 6, take away, well, we have no antibonding now. So we have a bond order of 3. So basically the 2 electrons that we're losing in O2 plus 2 are both coming out of antibonding orbitals. Therefore, this is actually making this particular molecule stronger.